All right, so now we're moving on to lesson 11.3, areas of regular polygons and circles. We're actually going to leave areas of circles for a few days down the road. So starting with regular polygons, remember what it means to be regular: equilateral, equiangular. All sides congruent, all angles congruent. Turns out there is one formula, a nice short little formula you can use to get the area of any regular polygon, whether it has 4 sides, 7 sides, or 613 sides. If it's regular, there's one short little formula. So I'm going to first derive the formula, which takes a bit of work, and then we'll see how to use it. So we're going to begin and end with this question. What's the area of this regular octagon if the radius is 13 centimeters? Round to the nearest hundredths. So that's where we're going to end. We're going to end by solving that question. So here are some regular polygons in red. And what I want you to see here is any regular polygon can be inscribed in a circle. So, the way I made these, of course, is I printed out circles, and for the triangle I just found 3 points equidistant around the circle and connected them with 3 chords. For the square, I had to find 4 equally spaced out arcs and connect those 4 points. And for the pentagon, I divided the circle into 5 congruent arcs and connected the 5 points. And there's a hexagon and an octagon. So any regular polygon, you can always imagine a circle that circumscribes it, that just touches each of the corners. Now this segment, if you ignore the triangle, this segment, we have a name for that on the circle. That's called a radius. For the regular polygon, that's also called the radius. So this circle has a radius right here. That's one of them. That's also going to be the radius of that square. So if that circle weren't there, that's the radius of the square. Now there's another segment that's going to be a new word that refers to the segment that connects the center of the polygon to a side of the polygon while it makes a right angle. So this little segment here, perpendicular to one side, is called the apothem. A-P-O-T-H-E-M. So if you've got a regular polygon, you can draw an apothem by connecting the center of the polygon to a side of the polygon so that it makes a right angle. So there's an apothem. Here's an apothem for the pentagon. Here's a radius of the pentagon. Here's an apothem for the hexagon. Here's the radius of the hexagon. So a little bit of vocabulary there. All right, so now to get into our proofs. I'm going to use pentagons as an example to try to come up with our formula. First of all, if this is a regular pentagon, we know these are all congruent sides. And if I add the radii, and I think about the fact that this could be inscribed in a circle, then I know all these radii are congruent. So that gives me 5 congruent triangles because of SSS. Every triangle here has 2 red sides, 1 black side, 2 red sides, a black side. So these triangles are all congruent. They're also each isosceles. So if we look at this one, that angle's congruent to that one because it's an isosceles triangle. But that triangle is congruent to this triangle. So whatever these angles are the same because of the congruent triangles and corresponding parts. This triangle is congruent to that one. Whatever those angles are, these angles are the same. And the same is true here, and the same is true here. So if we look at this picture, what we've just demonstrated is that the radius of the regular polygon bisects the angle of the regular polygon. See, this radius has cut the original angle into 2 congruent angles. This radius cut the angle into 2 congruent angles. Each radius is bisecting the angle. So that's just going to be an important fact to keep in mind. A radius bisects the angle. How about the apothem? What does it do? We know it makes a right angle. And I'm going to add 2 convenient radii. We know these radii are congruent to each other. And that makes these right triangles congruent to each other. We have those 5 congruency methods. In this case, hypotenuse leg, matching hypotenuse leg. So these triangles are congruent, which means all the parts of this triangle are congruent to the parts of that one, including the bottom side of this one has to be congruent to the bottom side of this one. And the purpose of that little picture is to demonstrate that an apothem bisects a side. So when you draw the apothem of a regular polygon, it always cuts the side in half. Radius cuts the angle in half, the apothem cuts the side in half. All right, now we can get to the formula. I'm going to draw the 5 radii again here. So this is a regular pentagon, and up above we said that these 5 triangles are all congruent. So if these 5 triangles are all congruent, well, that means if I could just get the area of one of them, then I would multiply by 5 and I have the area of the pentagon. So what does that look like? Let's see here. Well, there's an apothem. Here is a lowercase cursive s for a side length of my pentagon. So it must be the case that the area of this regular pentagon is going to equal 5 times the area of that shaded triangle, because we said they're all congruent triangles. So what is the area of any triangle? Well, it's 1/2 base height. So for this triangle, the base is s, the height is the apothem. So I'm going to replace the base with s and the height with a. The apothem is the height of that triangle. And we know when we multiply numbers together, the order doesn't matter. I can shuffle these around if I want to. Well, I want to. I'm going to shuffle these around. I'm going to do 1/2 times the a times the 5 times the s. I'm doing that because 5 times s represents something about this picture. If you look back at the picture, what does 5 times the side length represent? If this was 2 and we did 5 times 2, 10, what is that 10 representing? That's the perimeter. So I can replace this with just p. So the area of that regular pentagon must be 1/2 times the apothem times the perimeter. Now here's the great part. Suppose, instead of a pentagon, suppose this had been a hexagon. If this had been a hexagon, the only difference would have been this. We would have had a regular hexagon, 6 congruent sides, and we would have had 6 congruent radii. The only difference is we would have had 6 triangles, but still a side of S and an apothem of A. The only difference in the work would have been, instead of a 5, that would have been a 6. That would have been a 6. That would have been a 6. And what would 6 times S represent? That's the perimeter of this one. So this works for any regular polygon. So for any of these polygons, if I wanted to know the area of this red regular octagon, 1/2 AP. So in the next video, I'm going to go through 4 examples with you.